So, what does a thought actually cost? No, I'm not talking about calories. I mean, what's the real physical cost in the fundamental currency of the universe? Energy. It sounds a little out there, right? Well, today we're going to go on an incredible journey. We'll start with the global race to build the world's most powerful computers, and we're going to end up uncovering a fundamental law of reality itself, a law that connects one tiny bit of information to the entire cosmos. Spooky action at a distance. You've probably heard that before. That was Albert Einstein, one of the sharpest minds in history, talking about something in the quantum world that totally freaked him out. He just found it unsettling. But here's the wildest part. That very same spooky phenomenon is exactly what engineers are now racing to control. It's our perfect doorway into the bizarre and powerful world of quantum computing. And believe me, this isn't just some far-off theoretical idea. It is happening right now. There's a technological arms race underway, with governments and massive corporations pouring billions, literally billions of dollars into building these quantum computers. Why? Because these machines promise to solve problems that our best supercomputers today couldn't crack in a million years. The stakes are absolutely immense. Okay, so here's our game plan. We'll kick things off with that global superpower race, then we'll dive into the magic behind the qubit. From there, we'll uncover the hidden energy cost of information, get to know Landauer's ultimate limit, and then, for the grand finale, we'll connect it all back to the biggest scales imaginable, the entire cosmos. So, why the big rush? It's all driven by a really fundamental problem. Our computers today, for all their incredible power, are hitting a wall. They just can't properly simulate the complex, quantum nature of our universe. The whole idea really started with the legendary physicist Richard Feynman. He realized that if you want to truly simulate quantum mechanics, you don't just need a faster classical computer. You need a completely new kind of machine. You need a quantum computer, a machine that actually speaks the universe's native language. And the alphabet of that language isn't the good old bit, the 0 or 1 we all know. No, it's something much, much stranger and way more powerful. It's time to meet the qubit. The best way to get this is with a few simple analogies. A classical bit in your laptop is like a light switch. It's either on or it's off, 1 or 0. That's it. A qubit, on the other hand, is like a dimmer dial. It can be fully on, fully off, or any shade in between, all at the same time. Think of it like a coin on a table. That's a bit, either heads or tails. A qubit is that same coin spinning in the air. Before it lands, it's a mix of both heads and tails. This ability to be in multiple states at once, this spinning coin state, has a name: superposition. And that is the secret sauce. It's the property that allows qubits to hold and process an exponentially larger amount of information than classical bits could ever hope to. This is the first pillar of quantum computing's incredible power. The second pillar is entanglement. We're back to Einstein's spooky action. This is where two qubits become fundamentally linked, their fates intertwined. If you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. It's this bizarre connection that allows for powerful, parallel computations that are just impossible any other way. Okay, so we have these incredibly powerful, kind of mind-bending concepts, but here's the thing. None of this is just abstract math. Both classical and quantum computing are physical processes, and that means they have to play by the rules of the universe, especially the laws of thermodynamics. You already know this intuitively. When your laptop works hard, it gets warm. That heat is wasted energy. It's the physical price of all those calculations. But that brings up a really deep question. Is there a rock-bottom, unavoidable minimum cost? An absolute limit baked into the laws of nature itself? The answer is a resounding yes. And we know this thanks to the brilliant insight of physicist Rolf Landauer. He realized that information isn't some abstract, floaty concept. It is physical. It has to be stored on physical things, and because of that, it has a physical cost. And this insight led to what we now call Landauer's principle, a fundamental law of the universe that connects the world of information directly to the physical world of energy. So here's the key idea. Whenever you do something that's logically irreversible, meaning you can't undo it, you have to pay a price. The classic example is erasing one bit of data. Think about it. Once you set a bit to 0, you've lost the information of whether it was already a 0 or if it started as a 1. That information is gone forever, and nature demands a tiny energy payment for that act of forgetting. And here's the price tag. At room temperature, the cost to erase a single bit is about 3 times 10 to the minus 21 joules. Now, that number is so small, it's almost impossible to imagine. But the mind-blowing part isn't how small it is, it's that it's not zero. It is an absolute fundamental limit. You cannot build a machine, no matter how clever, that erases information for less energy. It's a law of the universe. And this isn't just a theory, it's actually been proven in a beautifully elegant experiment. Scientists trapped a single particle in a landscape with two little valleys, one for 0 and one for 1. To erase its memory, they first lowered the hill between the valleys, then just gently tilted the whole setup so the particle had no choice but to roll into the 0 valley. Just like that, the memory of its previous state was physically wiped out. And while they did this, they measured the tiny puff of heat that was released. What they found was incredible. As they performed the erasure more and more slowly and efficiently, the heat dissipated got smaller and smaller, but it never went to 0. It bottomed out at precisely the value Landauer had predicted. And just like that, it became a confirmed law of nature. A tiny energy cost for one little bit might sound trivial, right? But this principle has truly profound consequences, stretching from the absolute limits of our technology all the way to the very nature of the universe itself. So, if every single operation has an energy cost, and we know energy and time are linked in physics, does that mean there's a fundamental speed limit to computation? Yes, it absolutely does, and it reveals this fascinating trade-off that no one can escape. There's a fundamental link between temperature, speed, and energy. To make a computer more energy efficient by cooling it down, you are fundamentally forced to make it slower. Speed costs energy and efficiency costs time. You simply can't have the best of both worlds. Okay, prepare for a big leap here. We all know Einstein's famous equation, E equals mc squared. Energy and mass are two sides of the same coin. So, if erasing a bit has a minimum energy cost, does that mean a bit of stored information has a minimum mass? The answer, according to the mass energy information equivalence principle, is an astonishing yes. By combining Landauer's limit with Einstein's equation, you arrive at this stunning conclusion. Information isn't just physical, it actually has mass. At room temperature, a single bit weighs about 3 times 10 to the minus 38 kilograms. It's almost nothing, but it's not nothing. And this isn't just a quirky calculation. It gives real physical grounding to a profound idea from the physicist John Archibald Wheeler, which he called it from bit. The idea is that the it, all the physical reality of particles, fields, and forces, actually emerges from the bit, the fundamental yes or no questions of information, that the universe is, in its very essence, computational. And that leaves us with a final, mind-bending thought. We started with a very practical race to build a new computer, and we ended with the idea that information has mass. If Landauer's limit is the bridge connecting them, and if Wheeler's paradigm is correct, then what does that imply about the ultimate nature of our reality? If all things physical are, at their core, just information, what does that make our universe? Is it in the end just one giant information processor?